Well, we're in the National Petascale Computing Facility on the campus of the University of Illinois. This is a facility that houses one of the world's most powerful computers, not just for computation, but also for data analysis. So it's unique in the sense of it's the most intense data analysis system, as well as being one of the most highly parallel computers in the world, doing projects for science and engineering and other types of scholarly work for the nation's scientists. This is the 20th supercomputer that I've been involved with making work. I worked at Berkeley Laboratory. I was the general manager of a system called NERSC, the National Energy Research Scientific Computing Facility. And we had a number of supercomputers in NERSC. Before that, I worked at NASA Ames, again, making very large systems work. So when I heard of the Blue Waters project, I thought it was the best possible thing going on in high-performance computing, and it was changing the way people were thinking about these computers. It was converting from this idea, well, we'll just worry about the peak performance of the system and assume that I can make use of all that power. It turns out that that's not the case, that if you have to focus on what real work comes out of the system rather than some theoretical number. And that was the entire philosophy of the Blue Waters project, to get real science work done at a scale never before seen, faster than anybody else could do it. And I thought that was great, because that's really what motivates people for helping do this, what science impact is there. So I came and talked to some colleagues here, and eventually we worked out the fact that I came from California, the Bay Area, to Illinois about 5 years ago to make Blue Waters work. And I've enjoyed it very much since then. Illinois is a great place. Well, we have about 60 projects that use the system. And those projects come onto the system after a stringent peer review by different agencies. The largest amount of time is controlled by the National Science Foundation, and they have about 35 research teams from around the nation working on a large variety of different areas. So there are people that are doing astrophysics. How did the universe form? How did galaxies form? What happens when galaxies collide? Another example is a recently announced result, one of the first really groundbreaking results from the system, because we've only been running it in service now for about 6 months. And that result is how the AIDS virus infects a cell. And this is the first time such a high-resolution, complex simulation has been done. And that was in the cover of Nature in May. Another example is climate studies, severe weather, in terms of what's going to happen with our climate, but at resolutions that have never been done before, resolutions where actually clouds form at first principles rather than estimating how they form, kilometer resolutions. For the severe weather calculations, they are down to 10 meters, so that they can actually predict things like tornadoes or gusts of wind in hurricanes. The system was used to run the biggest simulation ever of a hurricane, Hurricane Sandy, and how that was different than other hurricanes, how the tracking was different and why it went the way it went. We also are doing a lot of chemistry applications, material science, and some other things like how does disease spread and other biomedical applications as well. Well, it's the largest system that Cray has ever built. It's about 50% larger than the next largest system, which happens to be at Oak Ridge National Lab in terms of size, number of cabinets, the scale of all the components. It is a system that has tremendous processing power. We term that power in terms of sustained performance, the time it takes to solve problems. And our mission here is to shrink the time it takes to solve problems by a variety of science and engineering teams into something that used to take years or decades into months or even sometimes weeks. So these are problems that cannot be done elsewhere. They're bigger than has ever been done before. They're more complex than has been done before. So that's our job. That's why this system is here at the university, serving the nation as a national resource. It also has more memory than any other system I know of in the world, 1.7 petabytes of memory that all can be accessed simultaneously by any one of the nodes. It has the most intense data system, not only because of the size of the data system, but also because of the bandwidth, the amount of data that can move back and forth from the parts of the system, the compute nodes, to online disk and then nearline storage. So it has almost a half of an exabyte of storage capacity in the system as well. And surrounding all that is one of the most highly connected systems in the world, with hundreds of gigabits of networking bandwidth coming from or leaving this facility, going to places in Chicago, and then being connected throughout the entire world. What we have here is the aggregation of many, many components together that are designed all to operate for single programs. But they're really made of the same components that are in your cell phones or your laptop computers. As a matter of fact, it's almost a fractal type relationship, because while in your laptop computer you have a processor that may have 2 or 4 cores in it, we have processors, 288 racks of processors that we use as a computational unit. They have about 800,000 cores that all operate simultaneously on the same applications. We have the interconnects that go between all those processors, so they all can communicate with each other, they all can coordinate the work. And they're put together then with linkages to our hard disk storage system, our rotating disk storage system. That's about 36 petabytes of storage, as opposed to 1 or 2 terabytes that you might have in your local machines. And then we have more storage that's nearby. It would be the equivalent of you plugging in a USB drive as a secondary drive. We call that nearline storage, and that's about 500 petabytes, almost half an exabyte of capacity, all connected together with a network, the same as you do on your cell phone or your other appliances. And to do that, you also need things like power supplies, like cooling. So if you think of the chip in your local computer, it has a heat sink on it, you have a fan. Well, we have a tremendous amount of infrastructure to cool the heat coming off of this machine, because it produces, it uses a lot of energy to do all these calculations as fast as it does. We also have a tremendous infrastructure for the power that comes into the building and then is distributed very efficiently to all the devices here. So in one way, it is just a much, much bigger combination of the equipment that you would have, but you have to be able to program it so it all operates simultaneously on a single application, which means that there's a lot of communication that goes on between the cores, between the processors, in order to do these simulations. So what we have is very, very tightly coupled communication across hundreds of thousands of cores, and that's how the programs are written on this system, with some specialized communication protocols. And this all happens very, very quickly so that we can make progress and be very efficient.